Yeah, welcome everybody. I'm Umesh Bhatirani. I quantum research project. So it's a real pleasure to welcome you all here. It's our second quantum industry day. The first one was online. So let me just say a couple of words about it, and then we'll get started. It's obviously a very exciting time for quantum computing. It's also a pretty challenging time. It's clear that we have got to move forward. It would be really good if we could find ways for all parties, academia, industry, research, national labs to work together and figure out how to do what they do best cooperatively. And so that's our goal in this Quantum Industry Day. So what do we have planned? Well, in terms of the official agenda, there's a really exciting set of speakers. We try to make it as far-ranging as possible, as deep as possible, and then there's a panel. But I'm hoping that it's a time between all this, in our breaks where there will be an opportunity to talk about how we can move forward and what this. So that's it. I hope you all enjoy it. So I should say that the first session will be chaired by Sandy Raj, who is the Associate Director of the Science Institute.
So it's a pleasure to welcome Steve Flammia from AWS. Steve's worked on a wide range of topics in quantum information, and today he's going to tell us about fault tolerance with bias noise challenges and opportunities.
Thanks, Sandy. This is really just a very, very broad overview talk about some relatively new ideas in trying to understand how we can improve quantum error correction and fault tolerance by taking advantage of physical aspects of noise that exist at the physical level, noise that exists at the physical level that has certain structure to it, and how we might be able to exploit that. And this is largely a totally open area. There's a bunch of relatively recent papers, but I want to try to frame this as just a few key highlights. And really, this is more meant to be an invitation for you to consider these questions and to contribute to this field. So what is physical noise? Physical noise, we know, if you believe quantum mechanics, which surely everyone in this room does, it's just described as a completely positive trace preserving map. But this is such a rich family of things. Real physical noise comes in lots of specific flavors. If you ask an experimentalist, they're not going to tell you CPTP map. They're going to start talking about other types of specific noise. They're going to mention things that the theorists in this room will recognize, dephasing or depolarizing noise, but also things like coherent rotations, crosstalk errors. So these are, but can I just have for a show of hands, because I was looking at the two programs, there was like the theory part of the program with people like Mark Zandri, and then there's the experiment part of the program with people like John Martinez. So these are on pretty wide ends of the spectrum. So I'm just not quite sure where to pitch this talk. So who in here is an experimentalist? Okay, and who's a theorist? Like, who submits to like Fox and Stock level? Okay, yeah, okay. So, all right, this is kind of a challenging audience. So I may ramble a little bit, but okay, sorry in advance.
Challenging to whom?
Me, but also probably the audience. I'm gonna try to. Yeah, let me try to elaborate. So, when I say crosstalk, if you're a computer scientist, just think correlations in the noise. But experimentalists, this can mean all kinds of sources of noise, from like some kind of ZZ coherent rotation type error to like DC flux crosstalk in a superconducting device or something like this. There's also leakage or erasure errors that can occur. This can be leakage from a computational subspace or into some other environmental degree of freedom. There's time and space correlated errors more generally, and there is a distinction between this and crosstalk, but I don't want to dive into that. There's this really cool paper by Google where they studied the impact of cosmic rays on one of their processors. I think this is a Sycamore processor, correct me if I'm wrong. And so, here the errors are both spatially and time-like correlated when they are precipitated by one of these events. And so we don't want these types of errors to destroy our quantum information in our devices. This is a type of noise that we may have to deal with. I mean, one way you might try to deal with this is build your quantum computer in a salt mine, many miles underground. And there's also spam errors or state preparation and measurement errors. And of course, this is not a comprehensive list because there's an infinite variety of types of errors. This is just a rough taxonomy that experimentalists like to keep in mind, and theorists as well.
You said CPTP now, so that's only for considering like Markovian errors.
Yeah, that's right. There's also non-Markovian noise.
Yeah. A lot of
Yeah. Oh, yeah. Well, it's CP on the scale of the universe, right? Or, you just go to the larger Hilbert space, and
I feel like the theorists.
or I guess it really only has to be positive if you really consider the universe, but that's a separate story. So, the theorists' view. This is a slide pitched at the theorists. Okay. This is a very small quantum computation when we think about what we want to be doing. We want to have 10,000 logical qubits, actually, but even 10,000 physical qubits would be great. And our circuits are quite complicated. This is just a circuit from this paper by Kerner et al. For extracting syndrome measurements in a distance 3 surface code. So a pretty simple thing as far as things go. And in order for us to understand what the noise looks like in these devices when we scale up beyond just a distance 3 surface code, we have to make various simplifying assumptions. And so to study quantum fault tolerance, both theoretically, both mathematically and numerically, theorists often simplify that list of noise processes down to basically 2 things: depolarizing noise and state preparation and measurement errors. And that's it. This seems like a really dramatic and vast simplification, and you might worry that we're not capturing essential features. So you might worry that we're kind of in this situation here on the right that, theorists are looking for their wallet underneath the lamppost because that's where the light is. And to some extent, I think that this is true. But you can also provide guarantees about general noise, theoretical guarantees against general noise by appealing to theory at the cost of some precision in your estimate of the threshold. But there are actually good practical reasons for doing this as well, not just the lamppost effect. So for example, quantum error correction tends to decohere errors. So you don't see superpositions of the bits that you've just read out from your syndrome measurement, right? Those things have decohered, they're in a classical memory now. Quantum error correction, there are several papers that have shown quantum error correction tends to decohere errors. Simulations of quantum error correction thresholds, like I said, they're only really possible when we make these assumptions. So it's not just that we're looking for it, it's just that there is no other place that we can look, basically, at large scales. There's also the fact that no experimental data on below threshold logical qubits exists that could otherwise guide our simulations. So we don't have medium scale quantum devices that are below threshold where we can just measure these error rates and use that type of information as input to other types of simulations. We do have medium scale quantum computers now, but all of them are above threshold in the strictest sense. Okay, so because real noise is complicated, we would like to find some abstractions that allow us to capture relevant physical features of noise and maintain and still be able to understand in a little bit more detail physical origins of noise that we might exploit in some way. And so here I want to advocate for more general notions of Pauli channels. So what is a Pauli channel? A Pauli channel is just any convex combination of Pauli errors. I guess this. Yeah, it's just any. This is the Krauss decomposition of some quantum channel acting on a state rho. It's just a convex combination of Pauli errors acting on the state rho. I'm assuming this is a qubit state, but we can generalize these types of channels. I don't necessarily require that these P's here are normalized, just that they're positive. If they're subnormalized, then I'm allowing for the possibility of leakage out of this qubit space. Okay, so if this is some effective qubit living in a larger Hilbert space, like maybe I've encoded a qubit into an oscillator or into the lowest 3 levels of a transmon qubit, then I can still look at these effective Pauli noise models in the computational subspace. So these P's are called the Pauli error rates. And I want to consider general probability distributions over all 4 to the n Pauli operators. I don't necessarily want to consider completely general ones because completely general probabilities over 4 to the n outcomes is also a pretty vast space. But we can parameterize these things by things like Ising models. And we can also study things where just some of these error rates are biased in one direction. Okay, and I'll give examples of that in a minute. So this is a really large class, but it's much, much simpler than the general class of quantum channels, or worse, non-Markovian noise. So I forgot to write it on the last slide, actually. But one very specific channel that I'm interested in is the class of biased noise channels. So biased noise channels are just ones where I have single qubit noise, which is independent. So I'm going to keep the independence assumption. But I'm going to assume that the Z error rates are much larger than either the PX error rates or the PY error rates. Okay, like I said, you could imagine more general things. Like I could imagine that that P of some string X is given by some local Hamiltonian, where these X's label these 2 n-bit strings that label the Pauli operators. And if this Hamiltonian is local, you expect exponential decay of correlations, and you might be able to still extract useful theoretical information from these models. But like I said, this talk is more of an invitation to studying these things. So I don't actually want to dive into this direction. I just want to talk about the simplest possible thing where the only noise correlation is that Z is dominant relative to X and Y. Okay, just the baby version. I'll also talk about erasures as well, though. So why should this model help? So a good intuition for biased noise is that if I fix the fidelity of a noise channel, so the fidelity, it turns out, if I have a single qubit channel, is just 1 minus P, where P is the total error rate between PX, PY, and PZ. Okay. So this is the fidelity of a quantum noise channel. And if I fix that, then the entropy of this noise channel is much lower if I fix this sum, but I push all the weight into Z errors, right? I mean, take this to the logical extreme. Maybe think if I exchange X and Z here, if I only had bit flip errors and I was promised this, well, we would be in the situation where we only need to do classical coding, and we know how to do this very efficiently, right? So the entropy is just a lot lower, and hopefully we can use codes that are tailored to this type of noise.
Entropy, do you mean the Shannon entropy?
Yeah, I literally mean the entropy of this of the distribution 1 minus P, PX, PY, PZ. So if I fix P and I push mass over to PZ, the entropy goes down. Okay. So intuitively, if I can find codes and decoders that are more sensitive to the likely errors in these scenarios, I should be able to much more efficiently protect against the likely errors. And so here's a diagram from a paper by Pablo Bonilla-Taides et al. This is a specific code, which is different from the surface code, but only in a very trivial way. You just do some local rotations on every second qubit. And what you find is that, at least this is for the phenomenological noise model, which for the experts in the audience doesn't require simulating circuit level noise, but really only just assigns state preparation and measurement errors together with independent gate errors to the noise. And if we take some notion of noise bias to be the ratio of PZ divided by this sum, PX plus PY, then as I tune this bias up, the threshold dramatically increases from values over here at around 0 bias, where the threshold is known to be about 4.5%. And when you have bias ratios of about 100, it rises to about 7% or even 8%. Biases of 100 are routinely observed in certain physical systems, like ion traps, other physical systems as well.
Sorry, is this assuming you just do one level of error, your lowest level of error correction is biased, and then after that it's unbiased? Or?
No, it's this is a surface code memory experiment, right? So like it's not an experiment. This is numerics, right? But there's a time history, and at every time you can have an error probability of a measurement error, or you can have a biased phase flip error, and with lower probability a bit flip or a Y flip error. And then you just decode, and what's the success probability for that memory experiment? And it's
With no
sensitive to the
concatenation.
bias.
There's
No, we haven't concatenated this into another code, but you could also, yes.
When you say standard decoder, means that you're doing XCCX code with
There's a-
or is that what-
Oh, no, this would be like the CSS code with a matching decoder that doesn't correlate between the X and the Z errors.
I see.
So these are the results that you get if you treat X and Z independently.
Okay, so then you're gonna do correlated decoder, and that's gonna push the.
Yeah, it would improve if you were to do that. This is kind of a baseline. Okay, to take maximal advantage of these ideas, like, so this is just one idea. There's several papers about this topic now. Another idea is to maximize the advantage of this bias. So the slide that I showed on the last, the results that the graph that I showed on the last slide doesn't include circuit level noise. Okay, and if you do a C0 gate, then you can map Z errors into X errors with a C0 gate. Okay, so you might worry that when I start to include circuit level noise, maybe the advantage of this bias is going to evaporate, or maybe I'm doing Hadamard gates, right? So I might convert high rate Z errors into high rate X errors during the course of a computation. And you are right to worry about this, but there are ideas for how to deal with this as well. So one idea is from this paper by Shruti Puri et al., where they consider the notion of bias preserving gates. They first take an oscillator and they encode a qubit into that oscillator into a specific code. This is a Kercat code in this paper. And they show that because of the physics of how this is encoded, the natural noise model that you get in the system actually is strongly biased towards dephasing. And you can design gates that preserve this noise bias, a universal set of gates that preserve this noise bias. Now, if you have this as your basic set of gates, you can concatenate this into a surface code and try to now observe a threshold. That was done in this paper by Andrew Dharmawan and colleagues, also Shruti Puri. And they showed that if you do this with an XZZX code, which we saw in the previous slide is sensitive to noise bias, and your bottleneck error rate is the error rate of your controlled NOT gate, they compared this scheme to what you get with standard surface code encodings. And they saw it like a factor of 2 improvement in the threshold with respect to this metric. So this is a factor of 2 gain that you get by first taking advantage of this idea of bias noise, and then this idea of bias preserving gates. Good, I'm almost done. There are some other ideas. Yeah.
So is there a sense, like, for arbitrary error correction schemes, is there a sense for, like, if you can engineer the error correction, like, for the ancillary circuits to preserve bias, like just engineer the stabilizer readouts or something? So
In general.
yeah, I mean, like, is there a sense in, like, where it probably should not preserve bias in general, or?
I don't think I understand the question. Like, I guess,
Like, do you think error correction just always would tend to remove bias from noise, or like, do you think
I
that?
think if you're naive about it, you will tend to wash out bias over time, because you're gonna, if you're just doing a bunch of random local unitaries, and you have a bare physical noise source, which is the origin of this asymmetry, you're going to scramble that origin somehow through the course of a computation. So you do have to be quite careful, which is, I think, one of the reasons why this took a while before people started really looking into this. There was an early paper by Alaferis and Fresco where they studied noise assuming bias, because superconducting circuits have biased noise in them.
Yeah.
And they designed a bunch of fault-tolerant gadgets that were really gadgety, for lack of a better word, in order to exactly preserve this bias. And I think it seemed like there was a lot of overhead and difficulty in trying to get these things to work. So it maybe didn't take off when it should have.
Yeah, great.
So there's another idea recently that's been floating around. So there are a few other gates. I'm kind of conflating something over here, this idea of error transparent gates, which is somewhat related. But actually the one that I want to highlight is a little more recent, the idea of erasure conversion. Erasure errors we can think of as being flagged general errors. If you have a general error, but you know its location, this turns into an erasure channel. And erasure channels, you can correct twice as many erasures as you can general errors with an error correcting code. So it would be nice if we had a systematic way to turn general errors into erasure errors that didn't cost us anything in terms of overhead. And again, the intuition here is that the entropy goes down when you do this. Like there's just a lot fewer ways to have these types of errors. So it should be easier to code for them and to decode them. So there are now a bunch of schemes like this that take advantage of the physical origin of the noise, erasure conversion in Rydberg atoms, or erasure conversion via ion metastable states, where instead of encoding into certain specific levels, you encode in some other level, which when it decays to a third check level, it emits a photon and you can detect this. So you can label when the errors happen and then correct them. There's also a dual rail encoded qubit inside superconducting qubits, where by adding some extra qubits and using a local encoding, you can protect against T1 errors in superconducting devices. This figure is from this paper by Qubits et al. And they show advantages by considering these erasure conversion qubits. So these are some other ideas in this vein. I'm almost out of time. So I just want to, this, like I said, this is an entreaty for you to think about these ideas. So exploiting noise bias for quantum error correction is in its infancy. I think the main challenges that we face in this field are there are basic physics questions, like how do we engineer noise bias while maintaining fidelity? My strong intuition comes exactly from this calculation that I sort of sketched for you, that if you can fix this number p, but you can push some of the noise into something that is has lower entropy, and you're an experimentalist, then you should absolutely do that. That should be your #1 thing that you can do. The theorists, on the other hand, need to think about this second question. What codes and decoders do we need to maximize the utility of this noise bias? So if this noise bias is towards dephasing, or if it's towards erasure, what can we do that's maximizing the hardware efficiency of this? And then lastly, I mentioned this paper by Alaferis and Preskill, but there's not a huge amount of work on protocols that are naturally fault tolerant or fault tolerant gadgets in the more computer science sense that can integrate some of this physics and some of the basic intuition that we get from studying specific physical systems. How can we integrate this stuff in a natural way? So I think this is an exciting field and it's pretty wide open. There's not a lot of stuff on it right now. So I hope many of the people watching this talk can contribute. Thank you.
Great talk, Steve. So I have another question. So it sounds from what you're saying in the end here that, normally we think of, okay, so for quantum computer, we want to know number of qubits, we want to know fidelity and gate fidelity. So if now you're saying, well, we could engineer the noise and make sure that it's biased. So is there a natural measure that you can put saying, well, instead of fidelity, let's look at something else. There's a measure of how good this implementation is, and how can you compare across them?
Yeah, I mean, my proposal, this has never been published anywhere, but my idea that should be, the idea that I would like to see if it works is exactly the entropy. Let's suppose that we have independent noise. Then we might be able to show specifically that families of codes, like surface codes, let's say, are sensitive only to this entropy as long as you're using optimized decoders. I mean, we've sort of shown this in a series of papers that I wrote with David Tuckett, where we looked at this trade-off with noise bias, but I think you could imagine a much stronger theoretical result along these lines. More generally, like I said, you could imagine a Gibbs distribution with a local Hamiltonian and exponentially decaying correlations, but where the entropy in this distribution is still extensive, but where it's substantially smaller. I don't really know what happens in these things. Like, you can definitely imagine tailoring the code in a decoder to study these types of models. I think these are realistic models for the types of noise that we see in devices. I would love it if there were some summary quantity, probably the entropy, which you could say really controls information, quantum information transmitted through this channel in a way that's maybe stronger than a Shannon theoretic type sense, but is practical in the sense that, you know, practical decoders and practical code layouts can achieve some notion of capacity, maybe not necessarily the actual capacity, which may be hard to calculate. But yeah, I don't know is the short answer. I'm kind of rambling here. But I think there's a lot of scope to answer this question, both from a theoretical and numerical side, and of course from an experimental side as well.
A quick comment more than a question. There was this paper by Pauli, and I forget the first author's name, about looking for natural metrics that decrease under error correction. I think in follow-up work and like slides I found somewhere, they considered looking at entropy of the error channels.
Yeah.
Because like diamond norm and fidelity don't, like they vary by orders of magnitude under error.
Yeah, they vary by orders of magnitude. I'm not sure that there's a metric that will always decrease. I mean, if you promise some features of the noise, then I think you can find such things. But as soon as you add some correlations, it's not so clear anymore.
You said all experiments are below threshold, but we are at 1.03, so you probably have something in mind. I was wondering.
You're at 1.03, meaning like you're.
Well, if you divide the logical array per round distance by 3, by distance 5, so we have.
You're very close to the threshold. Well, your 3 to 5 scaling paper shows an advantage, but you don't actually claim to be below the
No,
threshold.
we say we're at threshold.
Sure. Sure.
We're not above threshold. We don't claim to.
I'm being cautious when I say this. Okay, I'm very impressed by your work, by work of other groups as well that are approaching the threshold. The threshold, as you well know, is a really complicated concept.
We don't claim to be above threshold.
Sure, or below, whatever, beyond the limit. Yeah, sure. I'm being especially cautious when I say we don't have these things for the threshold. But yeah, with respect. To my colleagues that are at the threshold.
There's like somewhere you're not really thinking.
No. I'm not trying to pick a fight. I'm just trying to be cautious. I'm just trying to be cautious.
All right, thanks.
We thank Steve and